record on this computer. Okay. So let's see. Is this the HDMI cable? Why would you do that? Why would you do that? Why would you remove the HDMI cable? It's also really thick because the connection is that, or the socket over there is really tight. There we go. So what we're going to be talking about today is mazes in general. All right. Now, mazes are a kind of very popular pastime in the fall. It's actually kind of wonderful to talk about in the fall under normal circumstances because they can say, hey, you can go out to a hedge maze and try this or something like this, you know? And mazes generally have two kind of corresponding parts: generation algorithms, in which you make a maze, and maze solving algorithms, in which you solve a maze. There's the two links here, by the way, on the bottom of this page over here are excellent resources if you're interested in mazes and different ways of solving them and creating them. I like how much memory it takes up. And then just kind of how many solutions you can find, how many solutions it will find, all the shortest solutions, things like this. What's cool about this one is that this slideshow over here is it talks about the different ways that mazes are used to practice for your data structures and algorithm stuff, and that'll make it good for preparation. It's got some really cool demonstrations of how it goes about making these mazes. Some of them are also interesting because you can get very, very interesting kind of, mazes that look non-standard by creating a weave, where the things go under and over. So you can create, so mazes are pretty complex. In general, though, the algorithms we're talking about today will be able to solve all of these kind of mazes. Now, there's one basic solving algorithm that you can use, which is the wall following algorithm. Okay, and I'll be stepping off camera for a second for this one. But the wall following algorithm, or the right-hand rule or left-hand rule, whatever, is that as soon as you enter the entrance to the maze, you slap your hand on the wall, and then you proceed to not let go and just make your way through the maze, keeping your hand through this, and this will get you to the end. Believe it or not, so long as the exits are on the same wall, meaning that there is so long as there is a straight line that you can draw, which is a lot of mazes, by the way, right? However, if you're where doesn't this work? It won't work if basically you're in a kind of labyrinth situation where your exit through the maze is a detached elevator at the center of the maze or something like that. Also won't work if the maze is reconfiguring itself behind you. Like, those, and the other algorithm I'm going to talk about today, it will require you to, that's going to cause difficulty with that one too. We need different algorithms for that kind of thing. And God help you if you're in one of those mazes, in one of those, let's see if I can figure out what the game is. There's a 4D kind of maze game to get through. And that, wish I knew where, but it was, I'll find it at some point. But basically there's some experimental games that require you to do, basically simulate four-dimensional spaces or spaces that are non-Euclidean. Those are my personal favorites, where basically if you going down the wall, if you go down a hall and you turn around and go back down it, it's going to be different. Pretty nifty. All right. But anyway, in these kind of, what we're going to be using is we're going to be basically doing a non-recursive version of this recursive algorithm, which is a depth first search algorithm. And that basically means, and what that is that is similar to the way that Theseus solved his problems all those years ago, assuming if we were to pretend that Theseus, some mythological figure, was a real person. Okay. Got some couple of really famous pictures over here. But this isn't where we care about. It is the Labyrinth. That's what he's known for. Labyrinth. Okay, so he, in which kid, and who is he the son of? Is it also Zeus? Sometimes the king, son of Aegeus, or sometimes the son of Poseidon. Okay, got it. So it's also hard to keep track in mythology. Most kids are Zeus's. Anyway, so here we've got this beautiful picture of the labyrinth. It's a beautiful high-res scan, actually. Watch this. Oh, look at that. Yeah, really high-res. Amazing how amazingly high-res the scans of art are. And there he is going in the maze. And he's got pretty much everything he needs. He's got Ariadne's thread that the Princess Ariadne gave him. And he's got a sword, which is useful for not just for slaying minotaurs, but also making marks on the floor, which he can do because this is dirt. Interesting looking plants over there on the dirt. Wait a second, those aren't plants. So anyway, so if for those of you who aren't familiar with the mythology, he gets thrown into the labyrinth to what he needs to do for that particular chapter of his life is slay the Minotaur, which is the monster in the labyrinth that only he can get, which is this huge maze nobody's ever escaped. The Minotaur and mazes are so intertwined that basically that even in games like Dungeons and Dragons, spells like maze, which shoot people off into an extra dimensional maze, fail on Minotaurs. It's like written into the rules. It's kind of just baked into our mythologies these days. But how does he get through the maze? This terrible maze that no one had been able to escape before, built by the inventor Daedalus, who was the father of Icarus, who flew too close to the sun. I know my mythology. Well, it's this thread, and the idea here is that a thread helps you not get lost. You can use a thread to see where you have been, and you can use it. You can wind it back up to see where you've been, to backtrack, to go back to a point where there used to be a dead end. So he walks forward, he gets to a dead end. Okay, I've just wind up the thread and go back to a place I haven't been before. But how do I know if I haven't been there before? Well, what he can do is that he's got that nifty sword, so he could totally make some carvings on the ground, possibly on the wall if he doesn't mind damaging the sword too much, to make a mark to say, hey, this was a dead end. I've already been here. We can do the same thing with chalk on our end. If we've got multiple colors of chalk, we can kind of paint. We can make a mark on the walls to see where we've been with the chalk, right? And then if we need to backtrack, we just follow the chalk back while also laying down a different color to say we've already been here. If I, because we want to keep that data, we want to know that data, know that that the path that we've gone down is a dead end. So that is basically the algorithm we use here, and the algorithm that I give you the pseudocode for. Now, this assignment isn't too bad. If you follow the pseudocode, you'll have a not too horrible time solving it. But I'm gonna go ahead and go over the pitfalls that you may have had. Okay, so maze solving. So I've already downloaded these and booted up IntelliJ, but here is the assignment proper. Mazes and stacks. Okay. So, yeah, we are using a depth first search using the stack. It used to be worthwhile on Wikipedia, but they no longer have that on Wikipedia. So maybe check out Rosetta Code if you want to find that. But the depth first search is fairly straightforward. The idea here is that we will use this, instead of a thread, we'll have a stack. A stack. And the stack will keep track of this. The head of the stack is going to be the top of the stack is going to be our current position. Okay. So while maze exploration, wonderful misspelling on my part, is not done, and the stack is not empty, what we're going to do is we're going to peek to get our current position. And then we make a decision tree. If we can go north and haven't visited there yet, we push the location on to the north on top of our stack, and then we mark the current location as visited. So we say, hey, I want to go to there next turn. And then, but right now I'm going to work on, so I'm going to put that on the stack and I'm going to mark the current location. Okay. And then I try that for south, east, and west. Now, how can I tell whether or not I go north? Well, if there's a wall there, I can't go there. That's basically it. So if there's no wall, I can go in that direction. Another thing is, and finally, if I try all the directions, but there's either a wall or there's a mark saying I've already been there, then I can't go anywhere, so I'm at a dead end. In that case, I'm going to use a different color for this space to mark it, and then I'm going to pop off the stack. So there's three pieces of our source code. We've got the maze grid panel, and the cell. Okay. So right over here, this is the only thing that you actually have to work on is this one marked homework, which is solve maze. That is the only, so much like the rabbit and fox and rabbit code, you only have to target one thing, okay? Only one method here. Everything else is kind of for you to digest, but I'm gonna help you digest it right now. So maze, your main class, is a J-frame. This is the way that the most basic kind of graphics in Java are done, where you've got and yes, this is not identical to the code I gave out, but because of this part, I'm showing a bit of problem solving over here. So the frame of a window is, well, think of it like an actual window, like over here. The frame of the window is the stuff that the window occupies, right? You've got the thing I'm grabbing over here and dragging, that's part of the frame. These buttons on top and the title button and the title, which go over here, which I didn't put, that's part of the frame. This Java icon, part of the frame. The stuff inside of it is a panel. So what I do is, so when you make your frame, you add your panel to it. And then here I said, hey, make it an 800 by 800 pixels. Then I just have some black magic to do, which is I have to say, hey, when I hit the close button, make sure that we are going to, when I hit the close button, that's when you want to stop the program. I don't want the program to keep going, okay, in the background. This dot pack, which is just to kind of pack it all up, causes the window to be the preferred size and stuff, and then set visible to true, which seems like a silly thing that I have to specify that I want it to be true. I want it to pop up above everything else, but that is what it is. Okay. So now let's go into maze grid panel, which is the panel that I put in. It is a J panel, and I call it a grid panel because it's essentially a grid of stuff. Okay. What it is a grid of is cells represented by this array of cells. What is a cell? It's very simple. Cell is where you are. It's a single like square in your maze. You got each cell by default has 4 walls, north, south, east, and west, and a row and a column, which is the current location, which is where it is in the grid. This is just basically a way to change the color, which I have overridden for it, and how to paint whether or not it has walls. So in other words, this puts lines around it if it has a wall. And then basically this when we create the cell, it just sets it all up over here. So when you run this program, this is the constructor that gets called. And yes, I made bad practice by putting the constructor all the way at the bottom, but that's where everything interesting happens. So I say, hey, for a specific number, so for your X by Y maze, we're going to set it up in this window. This is the number of rows, this is the number of columns. And the layout is going to be like a grid of cells. So this is just more magic over here. And then I instantiate my array of cells, those little individual squares. And then I go through each of them and initialize them. and say, hey, they're part of this. Then I say, okay, generate my maze and then solve my maze. Now there's different maze generation algorithms and different maze solving algorithms, but I made up a very stupid one, which basically for generating your maze, which is for all the rows and for each row and column combination. So for each possible cell, if it's at the top left corner, just ignore it. Okay. If it's in the top row, remove all the east-west walls. If it's in the leftmost column, remove all the north-south walls. Okay, that way we can access kind of any insertion point over here. And then for every other square in there, what I do is I flip a coin at random. And I say, hey, if that coin comes up head, then what I want to do is I want to remove my north wall and the corresponding I want to remove my north wall, and for the square above me, remove its corresponding south wall, right? Makes sense? Got to make sure that since that is the same wall, right? My north wall is somebody else's south wall. Otherwise, if my coin flip comes up tails, remove my east wall, remove my west wall, and which is somebody else's east wall. Okay? And that's it. That's all I do. I'm basically just generating that. And what it creates is we've got kind of this diagonal pattern that goes through. So here is your work over here. So this is the beginning of that pseudocode I started out. We've got this stack of cells, right? The stack over here. Here's the starting location for it. And then initially what I'll do is I set the color of your starting point to green and your ending point to red. And then I initialize it by putting our starting point into the stack, because right, the top of the stack of where we are. So, and then instead of doing a while loop, what I recommend you do until you're very comfortable with the fact that your code works, you want to do this over here, which is like a for loop that runs the algorithm 10 times. And what I did over here is just to show you how this works, is that I get the current cell by where I am by looking at the top of the stack. I say set the color of the current location I'm at to blue. Mark where I am, mark it as blue. You can mark it as whatever color you want, except for red or white, because white is unvisited, right? You haven't been there yet, and red is our ending spot. So don't want to make it like that. And then I say, hey, and then this is just to show an example of how you move. What I do is I push the location of where I want to go onto the stack, which is inside the maze, I go current.row +1 and current.column +1. And that brings me south. So going down in the row. So this kind of is a bit mind-bendy, right? Okay, this is the first coordinate, and I add 1 to go down, which is so in so many ways the opposite of like the way you think, which is XY coordinates, right? Right? This is the first coordinate, but I'm moving vertically, right? But remember, we're working in arrays, which is row column notation, right? Row and column notation. And then for basically any kind of graphical interface in computer science, this location over here, this guy over there, that is 0, 0, right? In fact, this pixel over here on the top left of my screen, that pixel is pixel 0, 0, because it follows, because remember, under what this is just a 2D array. And so we're dealing with the 2D array, and that is why that this thing over here is 0, 0, because we're working in a 2D array. In terms of coordinate planes, right, we have different quadrants. This is the quadrant we are working in. So going down brings us in this direction, and so adding a value over here in this direction brings us down. Let's clear all those drawings off. Anyway, long story short, that's why why that brings us down. So here, what we want to do is you want to put in the pseudocode to kind of match this up. There is one helpful method I've already programmed for you, which is visited. Given a row and column, it will tell you whether or not you've been there if you've been coloring your things properly. So if the square is white or red, return full. will return false, right? The color set and the way, and again, how do you tell if you've been there? It's this line over here where you can color squares by setting the background of it. That is how you set the background of that specific square and you can create a color. Like over here, I could say maze 5 dot set background, and I could say color dot, which has a bunch of packaged colors we could use. So I could say color dot cyan, and now that would be whatever that color. Seeing that square is now cyan. Or I could say, hey, set it to a new color, and then come up with a like I want a ton of red, ton of what's the one? This is one. A ton of red, no blue. Sorry. Yeah, no green and a ton of blue, and you can kind of see that's predicting. It's able to figure out what color it's going to be by doing that. So you can do that. However, one thing you want to do, just as a helpful note, is that you might want to mark your path one color. It would be best if you mark your correct path one color, and the paths that you use to back up, the backtracking paths, whenever you pop, a different color. That way you can say, like I prefer gray to show that these were dead ends. Your end result, if you do that, your end result for the maze will look something along the lines of this. Your maze should basically look something along the lines of, hey, going through here. And all this area over here will be whatever your secondary color is, right? So you'll have this kind of triangular division, this half division, the division of your grid into this area, which is completely unexplored in the top, this area which is completely unexplored, your path, and your completely explored area. That's just the result of that. The extra credit is worth more than it actually says. So please, it says 5 points in the assignment, but I think that's a bit unfair. It should be more. The extra credit is to create a depth first search generated maze. That'll be worth 10 points, and that will create a solution that has a long, windy passage. Right. Any questions on this assignment? Any questions on assignment 5? Normally, I would go over that on Monday with the way things are progressing, but right, because people need more time on it. But also, since your exam is on Tuesday, Monday is going to be devoted for me going over the practice exam, right? Okay. All right. Well, with that, if you have any questions or you want to demo something, please let me know. Okay, return. Stop sharing and yoink this out.